Well, in this section, we're going to discuss, pardon me, the technique of integrating by the use of trigonometric substitution. And you'll see where the name comes from as we expand on this. But first we need kind of an introduction. And this technique is used when our integrands, that's what we're integrating, our integrands contain, several of these styles of square roots, okay? So for instance, if our integrand contains the square root of something of the form a squared minus u squared. Now, the a represents a constant and the u represents a variable expression. So u could be a 3x, so u squared would be 9x squared. And a could be a 2, so a squared is a 4. So it would be something like the square root of, for instance, the square root of 4 minus 9x squared is of that form. Okay, now what we're going to assume here, since we're talking about a squared, the value of a, whether it's positive or negative, doesn't matter, so we're going to assume it's going to be positive. And what we're going to do is we're going to and I'm going to build on this first, and then we'll go back and actually do some examples. So this is an introduction. We're going to let u be replaced. We're going to substitute u, even if it's a 3x, we're going to substitute u with an a times the sine of theta. So that's where the trigonometric substitution comes from. We're substituting u with a trigonometric function. And it's safe for us to assume that our theta is somewhere between negative pi over 2, negative pi over 2 and positive pi over 2. And the reason that's safe is that we get all values of sine there. And if we get all values of sine, then u can be any possible. We'll just make that assumption. I could go on about why, but the idea is that we get every potential value of sine. If we get every potential value of sine, then we can get every u value that's necessary. Okay. The next style of radical that we would be interested in is another square root of a squared plus u squared instead of minus u squared. Well, and once again, we're going to assume that a is positive, and our substitution in this case, and in a minute we'll see why, will be u is equal to a times tangent of theta. And in this case, because tangent of theta is not defined at negative pi over 2 or positive pi over 2, we're going to assume theta is between them, but not including those endpoints of negative pi over 2 and positive pi over 2. And the third style of integrand or radical would be, in the case, it'd be the reversal of what we have in the first one. That would be u squared minus a squared. Now, of course, the square root of u squared plus a squared is the same as the second one because that plus is commutative, but subtraction is not commutative. So here we would assume once again that a is positive, and our substitution here would let u be equal to a times secant of theta. And now, to make sure that things are safe here, and we really don't worry about these conditions clear over here on the right. We're worried more about these substitutions. We'll see as we go through here, but what we're going to assume in this case is theta is either between 0 and pi over 2, not including pi over 2, and that's actually when we have u is greater than or equal to a. And if u is less than or equal to a, then we're going to use the values of theta that it is greater than pi over 2, but less than or equal to pi. And that would be when u is less than or equal to the opposite of a, actually. I know like I said, the things over here are conditions that make these work, but we basically ignore those unless we're dealing with a definite integral. What's most important are these substitutions. Now, the big why, okay? Why those substitutions? Well, here's the why. In the case of the square root of a squared minus u squared, if we replace u with a times sine of theta, that's what we said up here. We're going to replace u with a times sine of theta. Well, if we do that, we end up with the square root of a squared minus, when we square u, we actually get a squared times sine squared theta. And then we'll notice that we happen to have a common factor of a squared here. And so underneath the radical, we can factor that and say that's a squared times the quantity 1 minus sine squared theta. Now, the significance there is that 1 minus sine squared theta is nothing more than cosine squared theta. And the square root of a squared, if a is positive, is just a, and the square root of cosine squared of theta, if theta is between negative pi over 2 and positive pi over 2, as we set up here, then cosine is positive, so the square root of cosine squared will be cosine of theta itself. So the issue is that with this substitution, okay, then we're safe. Then we're allowed, or we have a vehicle to eliminate the radical, and we have a much better chance of integrating that. Remember, this depended on the fact that cosine of theta is greater than or equal to 0 for the thetas that we named above, between negative pi over 2 and positive pi over 2. That was why we have that condition above. Now, in the second case, that is, if we had the square root of a squared plus u squared, well, if we make the substitution like I suggested above, that is, we'll replace a with a tangent, with a u with a times the tangent of theta, then this ends up being the square root of a squared, and when we square u, we get a squared tangent squared theta. Once again, we have a common factor of a squared, so we'll factor it out, and we have left behind, when we factor that a squared out, a 1 plus tangent squared theta. And it's kind of crunched up there. But 1 plus tangent squared of theta is nothing more than secant squared theta, isn't it? And so here we have a situation that we can take the square root of a squared and get a, since we know that a is positive, and secant of theta, okay, it's kind of the same kind of idea here. Secant of theta is positive if theta is between negative pi over 2 and positive pi over 2. Okay, and so that's what we needed to have happen here. And so we know when we take the square root of secant squared theta under these conditions, we simply get secant theta. So once again, we were able to eliminate the radical. Now, in the case of the square root of u squared minus a squared, we're looking for a substitution, and what I suggested is we would make the substitution for u as a times secant of theta. And so if we do that, we'll end up with, when we square u, a squared times secant squared theta, and then minus the a squared we already had there. Well, once again, we can factor out an a squared, and when we do, we'll have a secant squared theta minus 1 left. But secant squared theta minus 1 is nothing more than the tangent squared of theta. Well, the conditions we've set up ensure that the tangent of theta is going to be positive. That's those conditions way back up here ensure that. I'm not going to write that down here, but under those conditions it ensured, well, actually I should be a little bit careful. And maybe I will be a little more careful here. We actually have two cases, but normally we're only worried about the first case. We would actually get a times tangent of theta if u is greater than or equal to a. Because, and what we're using then is that theta is between 0 and pi. And in that case, excuse me, pi over 2, my bad. In that case, then the tangent's going to be positive. And so the square root of tangent squared theta is tangent of theta. But occasionally, and we won't worry about this often, occasionally we'd get the opposite of the tangent of theta, and that would be when u is less than or equal to negative a. And that's also the condition that we would have our theta between pi over 2 and pi. And under those conditions, the tangent is negative. So the square root of a negative number squared is the opposite of that negative number. That's where that negative sign comes from here. We actually get the square root of tangent squared theta is negative tangent theta. So normally, this is what we're worried about. We'll just say it that way, but we have all these possibilities. Well, now, I guess on the next page we'll start our first problem, and you'll see how this comes to play when we start doing this problem. As we see here, we're to evaluate the integral of x squared divided by the square root of 9 minus x squared with respect to x. And we may try several techniques, like the substitution technique that we're used to, and we're not going to have much pleasure out of trying to accomplish this. So when we see a constant minus some expression that we can think of as squared and underneath a radical, well, constant minus variable stuff squared, then we need to think about, we want to get a 1 minus sine squared theta, so we can replace that with cosine squared theta. So in this case, here's the idea. We want our u to be x, and of course, we see that our a would have to be 3. Now, what I said previously is that we want to replace our u, if you will, in this case our x really is what we're worrying about. We want to replace our x with a substitution, and that substitution needs to be a times, and that's a 3, the sine of theta. Now, the purpose in that, okay, let's go stop and think about the purpose in that, is that from there, I'm not going to write it out quite this way each time, from there, though, the square root we've got in the denominator would be the square root of 9, and if we replace x with 3 sine theta, that would actually give us a 9. When we square that, that would give us a 9 times sine squared of theta. And now we have this common factor of 9, so when we factor that out, we'll have a 9 times 1 minus sine squared theta. Okay, and this part can be replaced with cosine squared theta, and so we'll be in a position that we can actually eliminate that radical, because what we would end up getting when we look at that, we would end up getting a 3 times cosine of theta. So that clever substitution allows us to eliminate the integral. I mean the square root, which is a little bit of a problem here. So here's kind of how we set this up. I'm doing this in pieces, and we'll kind of do them more in whole in a moment. What I've done with this substitution, okay, what I've done is I've changed the radical in the denominator by that substitution, where I have nothing more than 3 times cosine of theta. But the problem is that I need to convert this into all, okay? So here's what I've got. This is what I started with. And the little routine above allowed me to replace that denominator. But if if I'm going to have success, I need to convert all to thetas, to theta stuff, okay, including the dx. Well, the way we're going to deal with the dx is we're going to look right up here. And since x is 3 times the sine of theta, then the derivative of x with respect to theta will be 3 times the cosine of theta, and of course dx is 3 times the cosine of theta d theta. So now we have a way to replace dx so that it's just theta stuff. And then we already knew that x is 3 sine of theta, so we can replace the numerator, which is x squared, with 9 times sine squared of theta. So all of that substitution is going to create an integral where we have in the denominator 3 times cosine of theta. And in the numerator, we have 9 times sine squared of theta. And we have dx that's replaced with 3 times the cosine of theta d theta. Now look at all that's going to happen. Okay, what we're going to end up with is the 3's here are going to cancel, the cosine thetas here are going to cancel, and so we're left with the integral of 9 times sine squared theta d theta. Well, that 9 will factor out, so we're left with 9 times the integral of sine squared theta d theta. Now, we've got this integral in terms of thetas that we need to complete. And so we go about our business completing these, okay, completing this, and we'll have to use the power reduction formula, won't we? So we'll replace sine squared theta with 1/2 times 1 plus the cosine of 2 theta, of course d theta. Now, we'll factor out the 1/2, and so we have 9 over 2 times the integral of 1 plus the cosine of 2 theta with respect to theta. Well, the integral of 1 with respect to theta is just theta. The integral of cosine of 2 theta, you can verify, is minus 1, the integral, and I made a big boo-boo up here, didn't I? I'm sorry for that stupid comment, boo-boo. Okay, this is a 1 minus cosine 2 theta, isn't it? This is a 1 minus cosine 2 theta. So we have a minus sign right here. The integral of cosine is a positive sign, but because of that 2 theta, we're going to have to, when we do our substitution, we're going to have to deal with the fact that we're integrating a cosine of 2 theta, plus our constant of integration here. Now, we're not quite finished, but let's distribute this 9/2. So we have 9/2 times theta minus 9/4 times the sine of 2 theta, plus our constant of integration. Now, here's the next part of the issue, the next part of the problem. We've got to go back to x's. I mean, our integral was about x's. So this is always going to be part of these problems. We're going to set up a representative right triangle, okay, where this is theta. Now, remember, we said x is 3 sine of theta. And so we can solve for sine of theta and say that it's x over 3. Now, sine in a right triangle is what? Opposite over hypotenuse? So we can represent this triangle by saying the side opposite theta is x and the hypotenuse is 3. Now, using the Pythagorean theorem, we could find this third side, and if you have any question about it, I suggest that you go about it. But we'll find through the Pythagorean theorem that this adjacent side ends up being the square root of 9 minus x squared. I mean, after all, if this side was side A, we would have a squared plus b squared is equal to c squared. And so in this case, we end up with a squared, which is what we're looking for. We're looking for a, is equal to c squared, which is 9, minus b squared, which is x squared. And so you can see then, since a squared is 9 minus x squared, a itself is the square root of. Okay. So now, what usefulness is that? Well, here's what we're going to have to do. We're going to have to first convert theta in terms of x. We're going to have to create a, here's what I'm trying to say. I'm getting all over the place because I did this in a funny way. We want to know how we can write theta in terms of x. And so the first issue is that we have that the sine of theta is equal to x over 3, don't we? And so that tells us that if we take the inverse sine of x over 3, we actually get theta. So down here in our integral, we can replace theta with the inverse sine of x over 3. Minus 9/4. Now here we've got another problem, because our triangle is in terms of theta and not 2 theta. But if we recall that the half angle formula for sine of 2 theta is 2 times sine of theta times cosine of theta. Now we have everything written in terms of sine and cosine of just theta. So we can go a little further, and I'm going to kind of jog over here with my equal sign. We have the 9/2 times inverse sine of x over 3. Make sure you understand why we got that. Minus, now we have a 9/4 times a 2, which is 9 over 2. Now, sine of theta, okay, was what? It's x over 3, isn't it? So we can replace the sine of theta with an x over 3. Now, how are we going to replace the cosine of theta? Well, look at the right triangle. The cosine of theta is adjacent divided by hypotenuse. And if we look at that right triangle, the adjacent side is the square root of 9 minus x squared. And the hypotenuse is 3. So we can replace cosine of theta here with the square root of 9 minus x squared, all divided by 3. Plus our constant integration that's out here. Well, where does that leave us? It looks like we ought to be able to simplify some here. We're certainly going to have a 9/2 times the inverse sine of x over 3. And when we look at what we've got here, this 3 times 3 is going to cancel with that 9, and so we're going to just have a minus 1/2. We could write it as a fraction, and we're left with an x times the square root of 9 minus x squared, plus our constant of integration. So we've completed the integral by using this trigonometric substitution. Now, of course, we need to do some other ones, and we'll do that following on the following pages.